Hello folks, my name is Kjell Prytz and I will discuss with you about the hearing senses and its connecting to physics, and in particular we will focus on the inner ear, which is in English usually named cochlea. We made a physical model of the inner ear, and that is the main objective here to present for you. We did this together with a student of mine, Lars Eine Jung, now working as a teacher here. Hearing senses is vast in physics application. It's more or less a physics classroom. And we will talk about that, and then we will give instructions for how we built the model, how the model may be built by yourself, and how we use it to improve understanding of the basic dynamics of the cochlea. This is the cochlea. And we will show that there is plenty of room for student exploration of this elaborated model, and also room for plenty of development. So some example of physics implications of hearing, and in particular mammal hearing senses. So we deal with the sound wave, and this sound wave propagates in all three different media. We will connect with the resonance phenomena, and also the nerve sensor cells is an electric process, so we actually connect to electric phenomena when studying the hearing senses. So let me start by a basic structure of the mammal ear, in particular the human ear. So it varies between different mammals, but for human we have an outer ear, which is collecting the sound and transmitted through an auditory canal about 3 centimeters in length, and this is sound propagation in air. Then the vibrations are received by the eardrum, and the objective of this senses is to transmit this sound wave in air to the cochlea, and the cochlea is filled with water. So that it's not possible to directly transmit from air to water, that just gives reflections. So for that reason, nature has invented the middle ear, which is the transmitter, and it's a sort of impedance matching, so to reduce the reflections. The inner ear is a very small piece. It has the size of a pea, and it has a spiraling form. It is, as I said, filled with water, and what is also appearing in the hearing senses is the balance senses here. So it's a very interesting topic to ask the students if they can figure out why nature has chosen this solution to place the balance senses in connection with the ear, because there is no direct connections between these two senses. Actually, nobody knows that, but it's quite interesting to discuss it. So the spiraling form is complicated. So to simplify, we will make a model of the cochlea where the cochlea is stretched out in a linear form. So the model looks like this. So we have a linear cochlea, and the key part of the cochlea, or in our analysis, is the basilar membrane. The cochlea is filled with water here, And the basilar membrane, that is a solid part. So what happens here is that when the sound vibrations are transmitted into the cochlea, these vibrations of the water will work as a driving force on the basilar membrane, and a resonance phenomena will appear depending on frequency, and this resonance phenomena will result in a transverse pulse of the basilar membrane, and it's this transverse pulse that triggers the sensor cells that send the signals to the brain. So each frequency has its particular place along this basilar membrane where this resonance effect appears. So and along this basilar membrane is connected to sensor cells, which is placed along the cochlea. So the brain gets information about the frequency of the sound wave in this way. And how does that work? Well, it works because the basilar membrane varies in stiffness along the cochlea, along the wave propagation. And it may be modeled like a set of parallel springs placed along the cochlea. And these parallel springs have different spring constants. So each spring has its unique natural frequency, meaning that the driving force that the vibration of the water constitute will cause a resonance effect at different positions along the cochlea. As stiffness decreases from entrance to exit, high stiffness at entrance, low stiffness at exit, meaning that at entrance, resonance occur for high frequencies. At exit, resonance occur for low frequencies. Signals are sent to the brain with this information. The brain interprets this as different frequencies, different tones of the sound. So within this interpretation, this model, we made a physical model of the cochlea. So we use this parallel spring interpretation of the basilar membrane to build a model of the cochlea. And these parallel springs we manage to introduce different spring constants. How did we do that? Our model looks like this. So we have a plexiglass box here. You can see the size of the box here compared to this function generator, a couple of 20 or to 30 centimeters in length. And this parallel spring modeling of cochlea is constructed using rubber bands. So it's rubber bands that constitute a spring. This rubber band may be strengthened with varying tension through a mechanical mechanism. So it's easy to vary the strength of the rubber band. So this the student can do themselves. Then we construct, so we have the highest stiffness as in reality close to entrance here. Here's a loudspeaker. This is the sound entrance. And we have the lowest stiffness farthest away from entrance as in reality. And then you see on this picture here, we have pictured the sensor cells. So we have different sensors along the cochlea. There are 3,000 to 4,000 of these sensor cells along the cochlea. So each connected with its unique nerve to the brain. So brain is included here in the picture. So then we would like to demonstrate now how it works. So we have 3 different movies for 3 different frequencies: a low frequency, middle frequency, high frequency. So then we have adjusted so that low frequency, then we expect the resonance effect far away from entrance. Here in the middle, high frequency, close to the entrance. So run the movie. Here we see resonance. Middle frequency. We see transverse vibrations in the middle of our membrane. And high frequency. We see vibrations here close to entrance. So this is what happens in nature. So now tension may be varied so that one can adjust the resonance frequency at different values, and one can also make this basilar membrane longer, so you cover a longer frequency range. What we think of is to use a complete sheet as the basilar membrane, as it is constructed in reality. And this complete sheet has then to show different stiffness along its length, as in reality. Another improvement is to change the form from linear to a spiraling form, as in reality. And the third improvement is to take into account the traveling wave phenomena, because the sound wave is actually a traveling wave. It's absorbed at exit. In our model, the sound wave is reflected. So this is actually crucial to construct a traveling wave, a model that make use of a traveling wave. So that is the end of my talk, and please take contact if you're interested in this so we can discuss this further. Thank you very much.